And I'm going to do a share screen here. So, hold on a second. Okay, can you see this, Bruce?
Oh yeah, here we are. Yep.
Okay, so what we're doing here is we're dealing with mathematics, and there's a particular mathematician here, an Indian's Srinivasa Ramanujan. But he has a lot of his mathematics and so forth came to him in, I'll almost say, a dream. He would just see these things. I view it as a type of meditation, that he was connected to the collective unconscious, the greater unity that's out there. And he saw pieces of it, which for him were mathematical formulae. So he ended up having a relatively short life, as we'll see. But my view of him is he was really one of the great mathematicians in the 20th century, but he lived for such a short time that other people didn't really understand what he did. And I think the utility of all the stuff he did really will become evident in this century, the 22nd century. He did his work in the 21st century, but it was really, the ideas will come to be used in the 22nd century. That's my 2 cents on what he did. Because in my experience, I've yet to really find any area of mathematics that is useless. Eventually, something happens and it kicks in. So we have a picture here of Ramanujan, and we have a picture here of G.H. Hardy. Hardy was an outstanding English mathematics professor at Cambridge in England, and Ramanujan just wrote him out of the blue, said, it was a long letter, and here's a bunch of things I've been working on. And Hardy, most of these things people, just ignore, throw away, whatever. Hardy looked at it and he said, this stuff is like so far out of it that it might even be true, and I don't have a clue as to how he proved this. And Hardy was a great mathematician, so you'll see. That's why Hardy had a huge impact on Ramanujan. So here we go. He was born in 1887 and he died in early 1920. So if I add these up, this is 33 years. But most of his work in mathematics was really done, I want to say in the 1910 to 1920 timeframe. And one of the problems we faced here is he was in this little Indian village out in the middle of nowhere. And so he really wasn't exposed to a lot of actual mathematics. There weren't any universities nearby that he could go to. So people have always said, what if when he was like 16 years old instead of 26 years old, he'd been exposed to what was happening in mathematics? What would he have done? He would have probably done times 10. But what he did was amazing all by itself. So keep that in mind. He has almost no formal training, to put it mildly, but he made substantial contributions to mathematical analysis, to number theory, to what are called infinite series. They go on forever and ever. They're continued fractions. They're solutions to mathematical problems that were considered unsolvable. He just solved these things instantly. No one knows how he did it. He just wrote down the answer. One of the things that he did was he dealt with infinite series, but for example, he would take an infinite series, 1 plus a half plus a fourth plus an eighth, and so forth. And so if you keep adding this up, you'd see with each term that you add to it, you're approaching the number 2. So he went ahead and he said, let me play some games with this. So he took 1 minus 1 plus 1 minus 1 plus 1 minus 1. So it's either 0 or 1 when you keep adding these terms up. And he showed that this equals minus 1/12. Minus 1/12, and all the numbers are between 0 and 1. I mean, where did this guy get this from? But he actually had his reasons for coming up with it. So here we go. And again, what he's doing here, I just view this as a type of meditation, as a type of linking to the collective unconsciousness here. So bear that in mind. The fact that he was in isolation was just because he was in the boondocks of India. He tried to interest the leading professional mathematicians in his work, but most of them couldn't figure out what he was talking about. In India, there's lots of people like this that are, people that write up things and then they approach some really well-known person who's a mathematician at a university and say, would you please read this? And they've just got piles of these things because India has so many people to it. And the problem was what he showed them was just simply too novel. It was too unfamiliar, and it was presented in some unusual way so that people really couldn't be bothered. They want to have things, handed to them on a spoon-fed so they can easily see yes or no what's going on. And that's why having someone like Hardy at Cambridge was unusual. Hardy also worked with another mathematician at Cambridge, Littlewood, and the two were really outstanding English mathematicians, and they both were in awe of Ramanujan. So in 1913, you can see, remember, he's going to die in 1920. So 1913, he was born in 1887. So that means he's 26. He started corresponding with Hardy, and Hardy, couldn't believe what he read, so he decided we've got to have Ramanujan come to Cambridge. So there were all kinds of new theorems that he'd written down. Hardy didn't have an idea how in the world did he prove these things. His only comment was that they were so bizarre that they had to be true. He said no one could invent these things. He must have somehow intuited these equations or theorems, and so it went. So during his short life, Ramanujan compiled nearly 3,900 results. I gave you an example of one just now. 1 minus 1 plus 1 minus 1 plus 1 equals minus 1/12. That was one of the things. He actually has other ones related to this. 1 plus 2 plus 4 plus 8 equals something like minus 1/3. Go figure. So a lot of these, again, were so novel and original and unconventional that they have they're named after him. There's a prime number called the Ramanujan prime. He developed something called the Ramanujan theta function. There's partition formulae, which relate to it's a type of Laplace transform, if that means anything to you. And then he not only developed these theta functions, but he developed Mach theta functions. Most of these results have been proven correct. But he just was writing these things down with no proof. No one had any idea, is this true or not? So now there's an actual Ramanujan journal which was established to publish work in all the areas that he influenced things. And he has a series of notebooks that we'll come to and so forth. And these have continually been visited by people since his death in 1920 for new ideas. That just shows you what he did in such a short period of time. As late as 2012, the researchers continue to discover that mere comments in his writings about simple properties or similar outputs for certain findings were themselves very profound and subtle results in number theory that remained unsuspected until nearly a century after his death. You know, he would just have these little comments there, and you know, no one paid attention to him. Why would you pay attention to some comment about, oh, it has some simple properties? It turns out no one had ever observed these properties before. Yeah. So he became one of the youngest fellows of the Royal Society in England and only the second Indian member. And he was the first Indian to ever be elected a fellow of Trinity College in Cambridge. So in 1919, his poor health, probably due to hepatic hemobiosis, some sort of complication from dysentery that he had, compelled him to return to India, where he died at the age of 32. His last letters to Hardy, written in 1920, show he was still continuing to produce new mathematical ideas and theorems. And he had a notebook which was lost for a period of time that contained discoveries from the last year of his life. And this was generated great excitement among mathematicians when it was rediscovered in 1976. So all of these notebooks have now been published, and proofs for every single thing, the 3,900 things that he did have been arrived at, but it's been done by people that are themselves incredible mathematicians, which just shows you who Ramanujan was. So let's go through his life briefly. Ramanujan literally means the younger brother of Rama, a Hindu deity. And he was born on the 22nd of December, 1887, into a Tamil Brahmin Inyagar family in present-day Tamil Nadu, the boonies of India. His father originally came from another district and worked as a clerk in a sari shop. And his mother was a housewife and sang at the local temple. And they lived in a small traditional home in the town of whatever. So absolutely nothing here suggests that Ramanujan is going to be a superstar mathematician. Absolutely nothing. The family home is now a museum. When Ramanujan was a year and a half old, his mother gave birth to a son, but the son unfortunately died less than 3 months later. In 1889, like 2 years after, 2 years old, he contracted smallpox but recovered. That's a miracle because there were another 4,000 people in the same area that died. Okay, he was one that made it. So that by itself was amazing. He moved with his mother to his parents' house near Madras, which is now called Chennai. His mother gave birth to 2 more children, both of whom died before their first birthdays. So he's basically an only child. When he was 5 years old, he was enrolled in the local school. After his maternal grandfather lost his job as a court official, he and his mother had to move back to where they came from, and he enrolled in primary school there. And when his paternal grandfather died, he was sent back to his maternal grandparents in Madras, or Chennai. He didn't like school in Madras and tried to avoid attending. His family enlisted a local constable to make sure he attended school. And within 6 months, he was back where they came from. He was out of Madras. So since Ramanujan's father was at work most of the day, his mother took care of the boy, and they had a close relationship. And from her, he learned about tradition and Puranas, how to sing religious songs, to attend pujas at the temple, and to maintain particular eating habits, all part of Brahmin culture. At his primary school, he performed well. Just before turning 10, he passed his primary examinations in English, Tamil, geography, and arithmetic with the best scores in the district. So there was a hint here that he was, quite capable. And so this would be in 1897. He was doing this. And so that year he entered a secondary school where for the first time he encountered formal mathematics. So at age 11, he'd already exhausted all the knowledge of the two college students who were lodging at his home. And he was later lent a book on advanced trigonometry, which he completely mastered by age 13, and discovered a lot of sophisticated theorems on his own. And by age 14, he'd received merit certificates and academic awards that continued throughout his school career. And he assisted the school in the logistics of assigning its 1,200 students to the approximately 35 teachers. Today we have software that does this, but he went ahead and figured it out. So he completed his mathematical exams in half the allotted time, and he showed a familiarity with geometry and with infinite series. And he was shown how to solve cubic equations in 1902. And based on this, he went off on his own, developed his own method to solve quartic equations, fourth order equations. And then in 1903, tried to solve fifth order equations, not knowing that it was impossible to solve them with simply radicals and numbers. This was something that Galois showed that he was simply not aware of, and it was done in a totally non-intuitive manner. So when he was 16 in 1903, he obtained a library copy of a synopsis of elementary results in pure and applied mathematics that had 5,000 theorems in it. So he just started drilling through this book and loved it. And then the next year, he independently developed and investigated the Bernoulli numbers, which we'll come to. And there also is something called the Euler-Mascheroni constant, which he calculated up to 15 decimal places. His peers at the time, remember this is when he's 16 years old, said they could rarely understand him, and they stood in respectful awe of him. So he had no one to talk to. When he graduated from the secondary school in 1904, what?
Were you like that when you were a boy?
No. Ramanujan was awarded the Rao Prize for mathematics, and he was introduced as an outstanding student who deserves scores higher than the maximum. In other words, he should get more than 100 for the work that he does. So he received a scholarship to study at the government's arts college, but he was so intent on mathematics, he couldn't focus on the other subjects and failed most of them. And then he lost his scholarship. So in 1905, Ramanujan ran away from home and stayed with somebody for about a month. And then he enrolled at this college in Madras, and there he passed in mathematics, choosing only to attempt questions that appealed to him and leaving the rest unanswered. But he performed poorly in other subjects such as English, physiology, and Sanskrit. So he failed his Fellow of Arts exam in December of 1906, and again a year later. And without a Fellow of Arts degree, he had to leave college and continue to pursue independent research in mathematics, living in extreme poverty and often on the brink of starvation. So there's absolutely nothing here that suggests he's going to be a star mathematician. In 1910, after a meeting between Ramanujan, who was then 23, and the founder of the Indian Math Society, Ramanujan began to get recognition in Madras's mathematical circles. So he became a researcher at the University of Madras. He married Janaki, who actually died in 1994. It's one of these arranged marriages. She was 10 years old and he was, let's see, 1909, 13 plus 9 is 20. So he's 22 and she's 10. It wasn't unusual for these arranged marriages. She came from a village close to this railway station, and Ramanujan's father didn't go to the marriage ceremony. But she stayed at her maternal home for 3 years after the marriage until she reached puberty. And then in 1912, she and Ramanujan's brother joined Ramanujan in Madras. So he stayed at a friend's house while he went door to door around Madras looking for a clerical position. And to make money, he tutored students at the local college who were preparing for their Fellow of Arts exam. In late 1910, Ramanujan was again sick. He had this hydrocele testis, but this was successfully operated on to clear up fluid buildup. So he was fearing for his health and told his friend to hand over his notebooks to Professor Modular, the mathematics professor at the college, or to the British professor Edward Ross at the Madras Christian College. He didn't want to have his work be forgotten. No one knew what his work was anyway. So after he recovered and retrieved his notebooks, he took a train to a city under French control. And in 1912, he moved with his wife and mother to a house in Georgetown, Madras. They lived for a few months. And in May 1913, he secured a research position at Madras University and moved his family close by to that. Still no great advances in math. In 1910, Ramanujan met the deputy collector who founded the Indian Mathematical Society, and wishing for a job at the revenue department where he worked, Ramanujan showed him his mathematics notebooks. And this gentleman replied, "I was struck by the extraordinary mathematical results contained in the notebooks. I had no mind to smother his genius by an appointment in the lowest rungs of the revenue department." So clearly he's been doing something on his own, and people are starting to find out about it. So Ramanujan had letters of introduction, and he went out to all these mathematicians in Madras, and some of them looked at his work and gave him letters of introduction to other people, like in the Indian Mathematical Society. But the one, for example, the guy who was in the Indian Mathematical Society, Rao, was very much impressed by Ramanujan's research, but he doubted that Ramanujan did the work. And so he mentioned a correspondence. Ramanujan mentioned a correspondence he had with Professor Saldanha, a notable Bombay mathematician, in which Saldanha expressed a lack of understanding of his work, but concluded he was not a fraud. So that impressed Rao. So how did they sort this out? Ramanujan's friend, Rajagopakrathi, tried to quell Rao's doubts about Ramanujan's capabilities. So Rao agreed to give him another chance, and he listened as Ramanujan discussed elliptic integrals, hypergeometric series, and his theory of divergent series, which Rao said ultimately convinced him of Ramanujan's brilliance. When Rao asked Ramanujan what he wanted, Ramanujan replied he needed work and financial support, and Rao consented and sent him to Madras, where he continued his research with Rao's aid, financial aid, and he had his work published in the Journal of the Indian Mathematical Society. So things are starting to break. So here's a sample of a problem. It's very difficult to explain this. So one of the first problems that he posed in this journal was to find the value of the following expression. So this expression would take the square root of whatever's between the parentheses, these out here. So the square root of 1 plus everything here. Well, what's in here? It's 2 times the square root of 1 plus 3 times. See, this is 2 times the square root. This is 3 times. This is 4 times the square root. So this goes on forever and ever. 5 times the square root and on and on. And they're all nested square roots here. So after 6 months, nobody was able to solve this problem. He thought it would be, you know, a piece of cake. So in his first notebook, he formulated an equation that could be used to solve this. These are all called radicals when you take square roots. They're to the half power. They could be to the third power or the fourth power or whatever. But his equation could be used to solve this, and he himself was able to provide some solution to it. So this is where he starts, is with things like this. Here's the equation that he actually put together. X plus n plus a equals the square root of a times x plus n plus a squared plus x times the square root of a plus x plus n plus a squared, and so forth. So this equation, if we plug in setting x equal to 2, n equal to 1, and a equal to 0, then if x is 2 and n is 1 and a is 0, we get 3 on the side. So 3 equals this mess of these square roots. So a times x is a is 0, so this drops out, and n plus a squared is 1 squared, which is 1, and then x is 2 times the square root of, and we work this out and so forth. So you can see what he's playing with here. On the one hand, it looks like you could, you know, somehow comprehend this stuff, but on the other hand, he's actually solving these things explicitly for what they are, and that is no small accomplishment. It's easy to write things down like this that you can't possibly evaluate. So he was writing down things he could all answer, and he just did this again and again. So he wrote his first formal paper on what are called Bernoulli numbers. Bernoulli was a Swiss mathematician. There are a number of Bernoullis, and he discovered that the denominators of the fraction of the Bernoulli numbers, there's actually an online website for online EIS. It's a series of it's a website of sequences of series. So you can look this thing up, OEIS, and you'll find out that all the fractions of these Bernoulli numbers are always divisible by 6. No one had realized that before. And then he came up with a method for calculating these Bernoulli numbers that are denoted by Bn based on previous Bernoulli numbers. So here's an example of this. If n is even, but not equal to 0, okay, so let's say n is 2, then B2 is a fraction. B2 is a fraction, and the numerator of B2 over 2 in its lowest terms is a prime number. Oops. Prime numbers. Well, 2 is a prime number, but we're talking about the numerator of B2, and the denominator of B2 contains each of the factors 2 and 3 once and only once. So the example we took here, we just have 2, we don't have 3. So if we took 2 times 3, we'd have 6. So B6 over 6. And then what he showed was that 2 to the 6th times 2 to the 6th minus 1 times B6, the 6th Bernoulli number, divided by 6 is an integer, and 2 times 2 to the 6th power minus 1 times the Bernoulli times B6 therefore must be an odd integer. So this is an example of something that takes him off into number theory, but also into these series that he loved. So he wrote a 17-page paper on these properties of Bernoulli numbers, and he gave 3 proofs and 2 corollaries, and there are a lot of flaws to it. And the editor of the journal said that his methods were so terse and novel, and his presentation was so lacking in clearness and precision that the ordinary mathematical reader is unaccustomed to such mental gymnastics and could hardly follow him. So but because he simply wrote down these numbers, that's why when they found these lost notebook, everyone was in awe. But it still took decades to go prove all of the things in these lost notebooks. No one doubted that they were true. It's just that there were no proofs. Just wrote things down. So there was another paper in 1912 that got him when he ended up getting a temporary job in the Madras accountant general's office, and he only lasted a few weeks there. But he applied for a position to the chief accountant of the Madras Port Trust. And he said, I understand there's a clerkship vacant in your office. I've passed the matriculation exam and studied up to the FA, the Fellow of Arts, but was prevented from pursuing my studies, further owing to several untoward circumstances. But I've been devoting all my time to mathematics and developing the subject. I can say I'm quite confident I can do justice to my work if I'm appointed to this post. So I request that you be good enough to confer the appointment on me. So, there he goes. And so there was a letter of recommendation from a math professor at a local college who wrote that Ramanujan was a young man of quite exceptional capacity in mathematics. And he, in fact, then was accepted to Class 3, Grade 4 accounting clerk, making 30 rupees per month. And so in 1912, I guess this is pretty good money. So he finished his work really quickly and ended up doing math in the time that was left over. In the spring of 1913, Rao and Iyer and Middlemast all tried to present Ramanujan's work to visiting British mathematicians from University College London. And one of them commented that these papers were just filled up with holes, their errors and whatnot. Maybe they were, maybe they weren't, who knows? But he said that although Ramanujan had a taste for mathematics and some ability, he lacked the necessary educational background and foundation to be accepted by mathematicians. So although Hill did not offer to take Ramanujan on as a student, he gave thorough and serious professional advice on his work, and this led him to drafting letters to the leading mathematicians at Cambridge University, and these are the best in the world at that time. So the first 2 professors, Baker and Hobson, returned his papers without looking at them. But on January 16th of 1913, Ramanujan wrote to G.H. Hardy, who he knew from studying his book, Orders of Infinity. There were 9 pages of mathematics in this letter. The letter is available online, so you can see it. And Hardy initially viewed Ramanujan's manuscripts as a fraud, that he stole the stuff and he's just wasting his time. But Hardy recognized some of Ramanujan's formulas, but others seemed scarcely possible to believe. Hardy found one of the theorems on integral representations amazing, while there were 2 examples of infinite series. The first result on integral representations had been done in 1859, but of course Ramanujan doesn't know anything. He just does this on his own. The second example was completely new to Hardy and was derived from a class of hypergeometric functions that had first been studied by Gauss and Euler. And he found these results much more intriguing than Gauss's work. Okay, so Gauss himself was one of the great mathematicians of the 1820s, 30s, 40s. There's an apocryphal story about Gauss, that Gauss was in a elementary school, and the teacher wanted to shut everybody up. So the teacher demanded that everybody add up the numbers 1 to 100. And when they had finished adding them up, they had to write the result down on a slate with chalk and then give it to the teacher. So after about 30 seconds, Gauss walked up and gave the teacher a slate. And the teacher said, "What is this, a joke?" And he looked at it, and what Gauss had done was, Gauss said, "Well, I have to add up 1 plus 2 plus 3 on up to 100. So he said, "Okay, let me just write this down backwards. I'll write 100 plus 99 plus 98 and so forth." So now he's written 1 plus 2 plus 3, and underneath it, he's got 100 plus 99 plus 98. So if I add up the first terms, they're 1 plus 100, that's 101. If I add 2 and 99, that's 101. If I add 3 and 98, that's 101. So he had 100 copies, 100 sums there that each added up to 101. So 100 times 101 is 10,100. But remember, he did this twice, so you have to divide by 2. So it's 5,050 is what 1 to 100 adds up to, 5,050. So Gauss did this, when he was 8 years old, And of course, he was probably the only one in the class who did it correctly, because everyone else is adding up all these numbers and making mistakes along the way. So Gauss was one of the great mathematicians in the early 1800s in Germany and anywhere in the world. Ramanujan is starting to show up as that caliber mathematician. Hardy said that he looked at Ramanujan's theorems on continued fractions. I was trying to describe continued square roots, but you could do the same thing for continued fractions. And Hardy said that he looked at these theorems and he didn't have a clue as to how in the world you could even begin to prove this theorem as being true. He was completely defeated, and he said they must be true, because if they weren't true, no one would have the imagination to invent these theorems. And that's what Ramanujan did. So Hardy asked his colleague Littlewood to take a look at the papers, and Littlewood was also amazed. And after discussing all this between Hardy and Littlewood, Hardy concluded the letters are certainly the most remarkable I've ever received, and Ramanujan was a mathematician of the highest quality, a man of altogether exceptional originality and power. And one colleague, Neville, later remarked that no one who was in the mathematical circles in Cambridge at the time can forget the sensation caused by Ramanujan's letter. Not one theorem could have been set in the most advanced mathematical exam in the world, which is what they did in Cambridge all the time. They would always be posing exams, and these questions were harder than any questions that they could pose in any exam in Cambridge. So that takes us to February of 1913. Hardy wrote Ramanujan, said he was interested in his work, and he said it's essential that I should see proofs of some of your assertions. So before his letter arrived in Madras, Hardy contacted the Indian office to plan for Ramanujan's trip to Cambridge, and the secretary of this committee for Indian students met with Ramanujan to discuss his overseas trip to England. Unfortunately, Ramanujan is a Brahmin, and if you're a Brahmin, you don't leave India. The rest of the world is unwashed. You're a Brahmin, you're above it all. So his parents were also opposed to his leaving. So in the meantime, Ramanujan sent Hardy a letter packed with even more theorems and said, "I found a friend in you who views my labor sympathetically." So to supplement Hardy's endorsement, Gilbert Walker, who was a lecturer at Trinity College in Cambridge, looked at Ramanujan's work and was amazed and urged the young man to spend time in Cambridge. So as a result of this endorsement, Rao, the mathematics professor at an engineering college, invited Ramanujan's colleague Iyer to a meeting of the Board of Studies in Mathematics to discuss what we can do for Ramanujan. And the board agreed to grant Ramanujan a monthly research scholarship of 75 rupees for the next 2 years. So he was at 30 rupees. All of a sudden, he's gone to 75 rupees. Incredible. So while he was engaged as a research student, Ramanujan continued to send papers to the Journal of the Indian Math Society. So in one instant, Iyer submitted some of Ramanujan's theorems on summation of series to the journal, adding the following theorem is due to S. Ramanujan, the mathematics student of Madras University. And finally, we get down to November of 1913, and Professor Edward Ross of Madras Christian College, whom Ramanujan had met a few years before, stormed into his class one day with his eyes glowing. And he asked his student, "Does Ramanujan know Polish?" And the reason was that there was a paper that Ramanujan had written that anticipated the work of a Polish mathematician. And this paper had just arrived at Ross's office. But Ramanujan had scooped him. So he said, well, maybe Ramanujan was stealing these ideas from this Polish mathematician. So in every quarter, Ramanujan would write up things, and he drew up theorems that made definite integrals more easy to solve. For example, definite integral is an integral over a specific range, like 2 to 4, something like that. Working off of Friulani's integral theorem, Ramanujan formulated generalizations that could be made to evaluate other integrals that no one had any idea how to evaluate.
You need to drink something.
I have to drink something. Okay. You want to go get me something? We don't have anything to drink. Give me a ginger ale.
Excuse us.
We'll excuse you. What? Get Jesse to. So Hardy's correspondence with Ramanujan soured after Ramanujan refused to come to England. So Hardy asked Neville, who was in Madras, to mentor and bring Ramanujan to England. And Neville asked Ramanujan why he wouldn't go to Cambridge. But things had changed. Ramanujan apparently had now accepted the proposal to go to England. And Neville said Ramanujan needs no converting now, and his parents have withdrawn their opposition to coming. Apparently what happened was Ramanujan's mother had a vivid dream in which Ramanujan was surrounded by Europeans, and the family goddess, the deity Namagiri, commanded her to stand no longer between her son and the fulfillment of his life's purpose. So finally, in March 17th, 1914, Ramanujan sailed, leaving his wife to stay with his parents in India. So remember, he's going to die, in just the spring of 1920. So he's only got 6 years left to his life. And this is where he makes these incredible splashes. He got to London in April, about a month later, and they took a car, which might be unique to Ramanujan. He'd probably never been in a car. And they went to Cambridge, England. And he began to work with Littlewood and Hardy. And after 6 weeks, Ramanujan, who was living in Neville's house, got his own residence, which is only 5 minutes away from where Hardy's office was. So now he's just going at it nonstop. And Hardy and Littlewood began to look at Ramanujan's notebooks. So Hardy had already received 120 theorems from Ramanujan in the first 2 letters, but the notebooks had many, many more results and theorems. And Hardy saw that some of these were wrong, others had already been discovered, and the rest were new breakthroughs. So Ramanujan left a very deep impression on Hardy and Littlewood. Littlewood commented, "I can believe that he's at least a Jacobi." Jacobi was a European mathematician who did amazing work along the same lines of Ramanujan in using series to solve equations of different sorts. And Hardy said he could only compare him to either Jacobi or Euler. Euler is, I believe, the most prolific mathematician ever to live. He just, everything he worked on, he was just amazing. So the end result was that Ramanujan spent nearly 5 years, thank you very much, in Cambridge. He collaborated with Hardy and Littlewood, who themselves were probably the 2 strongest English mathematicians of that era. And he published part of his findings there. So Hardy and Ramanujan had very highly contrasting personalities. Their collaboration was a clash of different cultures, beliefs, and working styles. In the previous few decades, the foundations of mathematics had come into question, and the need for mathematically rigorous proofs was recognized. This was driven by David Hilbert, who was arguably the greatest mathematician in the world at the time, and he felt that everything should be reduced to a set of axioms, and then from the axioms, you can rigorously derive proofs of whatever it is that you want to prove. What was amazing to Hilbert was that Gödel showed there were things that you could not prove that were lie outside the realm of these axioms or the foundations that you had. You know, so for example, there's a simple tautology. All men are blue, and no men lie. So you look at these and you say, well, if you're a man and you lie, then clearly saying you're blue is a lie. But saying this lie means that you're lying. So you've contradicted yourself in doing this. And the end result was that it was shown it was impossible. There would always be statements that you could make that would lie outside the axioms, outside the realm of mathematics. And Hardy himself was an atheist, and but he believed in proof and mathematical rigor. On the other hand, Ramanujan was a deeply religious Brahmin, and he relied very strongly on his intuition and insights. He would just draw on these things. You know, Hardy really couldn't meditate. And that's all that Ramanujan did, was he would meditate and come up with new theorems, new insights. So Hardy tried his best to fill the gaps in Ramanujan's education and mentored him in the need for formal proofs to support his results. A lot of times, because Ramanujan was from such a poor background, he would have a slate and with some chalk, and he'd be doing all of his work on the slate and wiping it off and putting some more things on there. And then eventually he would get done and he'd just write down on a piece of paper, because paper was very expensive. He'd write down what the theorem was. So there was no proof. It was on the slate, but he'd erase the slate. So that was what he did. But Hardy tried to not to hinder Ramanujan, but it was always a battle of getting to drag out of him how in the world did he prove these things. So in March 1916, he received the Bachelor of Arts by research, which is the predecessor of getting a PhD degree, for his work on highly composite numbers. And this had been already published in the Proceedings of the London Math Society, which is one of the premier math journals in the world at the time. And the paper that it was published was more than 50 pages long and had all kinds of properties of these numbers. So Hardy disliked this topic area, but remarked that it engaged with what he called the backwater of mathematics. And in it, Ramanujan displayed extraordinary mastery over the algebra of inequalities in this. So this is a tip-off that he's starting to really roll. In December 6th of 1917, so this is when he's, whatever it is, 30, he was elected to the London Mathematical Society, and in May of 1918, he was elected a Fellow of the Royal Society, and it was the second Indian to be admitted there. The other one was in 1841. And so at age 31, he became one of the youngest fellows in the Royal Society's history. And he was elected for his investigation in elliptic functions and the theory of numbers, and became the first Indian to be elected a fellow of Trinity College, Cambridge. So he did all this he went there in 1914. In 4 years, he's now at the pinnacle of everything. Now, he had lots of health problems throughout his life. And his health worsened in England, but he couldn't keep up with the strict dietary requirements of being a Brahmin. And this is World War I, so there's rationing that takes place. So he was diagnosed with tuberculosis, had a severe vitamin deficiency, and was confined to a sanitarium. And he actually attempted suicide in late 1917, early 1918 by jumping on the tracks in a London Underground station. But Scotland Yard arrested him for attempted suicide, which was a crime. But Hardy intervened and he was released. So finally, in 1919, Ramanujan returned to India, to Madras, where he died in 1920 at age 32. But he continued doing his math right up to the end, filling sheet after sheet with numbers. So now let's go off and look at G.H. Hardy. He was born in 1877, died in 1947. He's was an outstanding mathematician in number theory, but also in mathematical analysis. He did some work in mathematical biology, which is an area of population genetics. You know, we get this with COVID, for example, and how things spread. But Hardy is known to those outside the field of mathematics for a book he wrote in 1940. It's an essay, A Mathematician's Apology, often considered to be one of the best insights into the mind of a working mathematician, written for the lay person. And it's eminently readable. I encourage you to take a look at it. So starting in 1914, Hardy was the mentor of Ramanujan, and Hardy almost immediately recognized Ramanujan's extraordinary untutored brilliance and they became close collaborators. In an interview by Paul Erdős was one of the great mathematicians of the 20th century. Erdős published over 400 different papers that are all fundamental papers in some area of mathematics. Could be number theory, could be, you name it. If Erdős thought about it, it meant that the problem was worth thinking about and was serious. And he said that when you prove something, there was the best proof, and then there were all these other proofs that people came up with that weren't quite as good. And he said he was always looking for the best proof. He said that was in the book that God kept. So that's who Erdős was. Erdős was being interviewed. Hardy asked, Erdős asked Hardy what his greatest contribution to mathematics was, and Hardy said it was the discovery of Ramanujan. Okay, so in the lecture on Ramanujan, Hardy said, "My association with him is the one romantic incident in my life." So in mathematics, there's a distinction between insight and formulating or working through a proof. And Ramanujan proposed just a huge number of formulae that could be investigated later in depth. And Hardy said that Ramanujan's discoveries are unusually rich. There's often more to them than initially meets the eye. That's what people have found again and again. As a byproduct of his work, new directions of research were opened up. So, for example, the most intriguing of these formulas includes infinite series for the number pi. Well, many infinite series that you use to calculate pi term after term, each term you get one additional decimal place, okay? The series that Ramanujan came up to calculate pi, the very first term gave pi to 6 significant figures. The second term added another 6 to 7 significant figures. In other words, the series that he had just in the first terms were so phenomenally accurate that they were just gilding the lily out in the 10th significant figure to pi. That's who Ramanujan was. The series for pi that converges extraordinarily rapidly and forms the basis for some of the fastest algorithms used to calculate pi. So if you just truncate this at some point, the very first term gives you 9801 times the square root of 2 divided by 4412. And this is pi to 6 decimal places. If we just take the first 2 terms in this series, it's correct to 14 decimal places. One of Ramanujan's remarkable capabilities was how he could rapidly solve problems. Here's an anecdote that illustrates this. Imagine you're on a street with houses marked 1 through n. There's a house in between x, such that the sum of the house numbers to the left of it equals the sum of the house numbers to the right of it. If n is between 50 and 100, what are n and x? So there's many problems to this. Ramanujan thought about it and gave the answer with a twist. He gave it as a continued fraction. The unusual part was it was a solution to a whole class of problems, and the author was astounded and asked how he did it. And Ramanujan said, "Oh, it's simple. The minute I heard the problem, I knew the answer was a continued fraction. The only question was which continued fraction, and then the answer came to me." So here you have it, how this guy thinks, or how he channels things from the great beyond. It just immediately comes to him. In 1918, Hardy and Ramanujan studied this partition function extensively, which I won't go into, but they gave what's called the non-convergent asymptotic series that allows you to permit to do exact computations of the number of partitions of an integer. And in 1937, Hans Rademacher refined their formula to find an exact convergent series. They had a non-convergent asymptotic series. He came up with an exact convergent series, but he wouldn't have done it unless Ramanujan and Hardy had pointed him to this new method for looking at this. So in the last years of his life, Ramanujan discovered what he called Mach theta functions. And for many years, these functions were a mystery, but after 100 years, we now know that they're holomorphic parts of the harmonic weak Moss forms. So there you have it. That would make a mathematician happy to know this is what Ramanujan was working on at the end of his life. Although there are numerous statements that could have borne the name Ramanujan conjecture, one was highly influential in later work. In particular, the connection of this conjecture with conjectures of Andre Y in algebraic geometry opened up new areas of research. So Andre Y was looking at algebraic geometry, and he felt that there were intrinsic linkages between this and number theory. Don't ask me why he thought this was the case. That's why he's Andre Y. So Ramanujan was the one that actually planted the seed that Andre Y picked up on to do this. And the Ramanujan conjecture is an assertion on the size of a so-called tau function, which is the generating function of the discriminant modular form delta of Q, which has a typical cusp in the theory of modular forms. And it was finally proven, this is the conjecture of Ramanujan, it was proven in 1973 as a consequence of Weyl's conjectures, but the proof itself was so incredible that the person, Pierre Deligne, won a Fields Medal in 1978 for this work. This is the Nobel Prize of Mathematics. So Ramanujan throws off this thing as a conjecture, and 50 years later, this guy is able to carry out the proof that shows, yeah, you're right. But he wouldn't have done that unless Ramanujan had actually started it all in the first place. Ramanujan wrote a paper called On Certain Arithmetical Functions, and there was a so-called delta function that arises in this Ramanujan tau function. So he had many congruences for these numbers, such as 1 plus p 11 mod 691 for primes p. So p is a prime number. This is the 11th prime here, p11, the 11th prime, and then modulo 691. That is, we use a circular arithmetic system. So we go 0, 1, 2, 3, 4, 5. When we get up to 691, we go back to 0. So you think of the numbers as laid around on a circle. We run around in a circle. And this congruence and other things like it that Ramanujan proved inspired this other Fields medalist, Jean-Pierre Serre, to conjecture that there's a theory of Galois representations that explains these congruences and more generally all modular forms. But again, he wouldn't have done it unless Ramanujan had suggested it to him in the first place. So he keeps throwing these things out, and these people start to prove them, but then the proof itself is formidable. The proof of Fermat's last theorem, Fermat's last theorem is the following: x to the n plus y to the n equals z to the n. So when n equals 2, x squared plus y squared equals z squared, there's lots and lots, there's an infinite number of solutions. 3 squared plus 4 squared equals 5 squared. 5 squared plus 12 squared equals 13 squared. It's called the Pythagorean theorem. But what Fermat observed was that when you make n not equal to 2, that there is no proof. that is with integers. No integers will solve this. So x cubed plus y cubed equals z cubed. Any other power than 2 is the only power of 2 is the only one that works. This is Fermat's last theorem. And what happened here was that the proof of this theorem, which was done in the middle 1980s, involved first interpreting elliptic curves and modular forms in terms of these Galois representations that were touched on here. And because of this is all really due to Ramanujan starting this stuff off. Because of this, there wouldn't be any proof of Fermat's last theorem. It's just who he was. He just threw these things off. While he was in Madras, Ramanujan recorded the bulk of his results in 4 notebooks of loose-leaf paper. They're mostly written up without any derivations, and this is the origin of the misrepresentation that Ramanujan was unable to prove his results and simply fabricated these final results. This one mathematician reviewed these notebooks. I believe there's 4 notebooks, and said that Ramanujan most certainly was able to prove most of his results, but just chose not to record the results in his notes. And it could be because paper was expensive, because he used a slate. No one knows. The problem is there's no proofs there. So the first notebook has 351 pages, 16 chapters roughly. Second one has 256 pages, 21 chapters. Third one is a short one, just 33 pages. And this inspired all kinds of papers by people. And then there's a 4th notebook that was just discovered in 1976 with 87 pages. This is the so-called lost notebook, because these were all available when he died in 1920. This one was misplaced and somehow came up in here. So Hardy himself wrote papers exploring all this material, as did many others. And you can order these things now on Amazon and see what Ramanujan did. One of the things about Ramanujan is, just to give you who he is the number 1729. This is known as the Hardy-Ramanujan number. Hardy went to see Ramanujan when he was in the hospital. So Hardy said, I remember going to see Ramanujan when he was ill. I wrote in taxi cab number 1729, and I remarked to Ramanujan that number seemed to me to be a rather dull number, and I hoped it was not an unfavorable omen. And Ramanujan immediately replied, no, it's a very interesting number. It's the smallest number expressible as the sum of 2 cubes in 2 different ways. So you stopped it and asked yourself, what did he do? So Hardy went ahead and quoted Littlewood as saying every positive integer was one of Ramanujan's personal friends. So here's how to write 1729. It's 1 cubed plus 12 cubed. Well, 12 cubed is 1728, and 1 cubed is 1. Here's 9 cubed, which is 729, and 10 cubed, which is 1,000. So 729 plus 1,000 is 1729. Ramanujan knew this instantly. So these are called taxicab numbers. In his obituary of Ramanujan, Hardy observed that Ramanujan's work primarily involved fields less known even among other pure mathematicians. So his insight into formulae was quite amazing and beyond anything I have met in any European mathematician. It's perhaps senseless to speculate as to his history had he been introduced to modern ideas and methods at age 16 instead of at 26. It's not extravagant to suppose he might have become the greatest mathematician of his time. What he actually did is wonderful enough. When the researches, which his work has suggested, have been completed, you'll probably see a good deal more wonderful than it does today. He combined a power of generalization, a feeling for form, and a capacity for rapid modification of his hypotheses that were often really startling and made him in his own particular field without a rival. The limitations of his knowledge were as startling as how profound they were. Here was a man who could work out modular equations and theorems to orders unheard of, whose mastery of continued fractions was beyond that of any mathematician in the world, who found for himself the functional equation of the zeta function. The zeta function is 1 over zeta to the n power, where zeta is a complex number. And you sum this, zeta goes, n goes 1, 2, 3, 4, etc. And the dominant terms in many of the most famous problems in the analytic theory of numbers. And yet, Ramanujan had never heard of a doubly periodic function or of Cauchy's theorem in complex analysis, that the real and imaginary parts of a complex function are related to one another as partial derivatives. And he indeed had the vaguest idea of what a function of a complex variable was. He just didn't live long enough to learn about these things. Hardy commented that on the 15 theorems in the first letter that Ramanujan sent him, the first 13 were correct and insightful. The 14th is incorrect but insightful, and the 15th is correct but misleading. And so this was one of the most fruitful he ever made, since it ended up leading us all to our joint work on partitions, this 15th one. And you can look at his letter. It's all available online. When asked about the methods Ramanujan used to arrive at his solutions, Hardy said they were arrived at by a process of mingled argument, intuition, and induction, of which he was entirely unable to give a coherent account. Hardy said he'd never met his equal and could compare Ramanujan only with Euler or Jacobi, which are two of the greatest mathematicians of earlier times. And Hardy thought Ramanujan worked in a 19th century style while arriving at correct formulas that was more important than systematic formal theories. Hardy thought his achievements were greatest in algebra, especially in hypergeometric series and something else that scrolled off. So it's possible that the great days of formulas are finished and that Ramanujan ought to have been born 100 years ago, but nonetheless, he was by far the greatest formalist of his time. There have been a good many more important, and I suppose one must say greater, mathematicians than Ramanujan during the last 50 years, but not one could stand up to him on his own ground. In playing the game on which he knew the rules, he could give any mathematician in the world 15. Now, the thing about this is, just like in mathematics, there's certain things that come in style and that are in vogue. And so what's happened in mathematics is they've moved away from cranking out these formulas like Ramanujan was able to do with these continued fractions and series and so forth. And instead, they go to more abstract representations dealing with mapping this function to that function and so forth. But there's no actual, calculations per se. It's all a qualitative description. It could very well be that things swing back, and that what Ramanujan did that was not in style now is going to become in style. And that's what I think is going to happen here. What he did was incredibly insightful. So we'll see. That's my 2 cents. He discovered fewer new things in analysis, probably because he lacked the formal education and he didn't have books to learn from it, but he rediscovered many results, including the prime number theorem, which relates to the density of primes. Primes are scattered throughout all the numbers. In analysis, he worked on elliptic functions and the analytic theory of numbers. And in analytic number theory, he was imaginative as useful, but much of what he imagined was wrong. And Hardy blames this on the inherent difficulty of analytic number theory, where imagination led many great mathematicians astray. They they would go after things that appeared to be true, and in fact, they weren't true. In analytic number theory, rigorous proof is more important than imagination, which is the opposite of Ramanujan's style. So his one great failure that Hardy pointed to was he knew nothing at all about the theory of analytic functions, which are functions that are complex valued. So Littlewood reportedly said that helping Ramanujan catch up with European mathematics beyond what was available in India was very difficult, because each new point mentioned to Ramanujan caused him to produce original ideas that prevented Littlewood from continuing the lesson. So Rao said, as for his place in the world of mathematics, we quote the following: Paul Erdős has passed on to us Hardy's personal ratings of mathematicians. Suppose we rate mathematicians on the basis of pure talent, on a scale of 0 to 100. Hardy himself gave himself a score of 25. Littlewood got a score of 30. David Hilbert got a score of 80. And Ramanujan got a score of 100. In 2011, at this lecture in Madras, over the last 40 years, nearly all of Ramanujan's conjectures have been proven. There's been a greater appreciation of Ramanujan's work and his brilliance, and that his work was now pervading many areas of modern mathematics and physics. So there you go. You can see there's something mystical here about this guy.
Wow.
He lived a very short life, but his impact was incredible at the highest levels, and so it goes.
I think you can really see how it's a question of hardwiring and what that means, what the implications are for mathematics itself, that it's, as who is it who said, I think it might have been Einstein, the order is there, it's not in our minds. And I think it was,
Einstein said too that the problem is that you can find many paths, but the hard thing is there's really only one path that's the correct path. And finding that one is easier said than done.
I knew somebody who was very brilliant, and
some good YouTube videos on Ramanujan going through some of these things, like I mentioned, like how could you have 1 + 2 + 4 + 8? That's clearly everything you're adding up there is all positive, and it equals -1/4. Now, how did Ramanujan come up with that? And he has his own ways of doing it, but it just shows you he just thinks totally different, outside the box.
right. Well, I knew I had a friend who had a brilliant mind. He was so different in how he thinks. It's like he was in research in Ontario Hydro, and they were working on problems, and he'd go to the washroom and come back with the solution.
Right.
Mhm.
And people couldn't even begin to write down what the problem is.
Yeah, and the thing is that he was so fast. Like I could be talking about something, and in a flash, he'd figure it all out, and then he'd tell me what I was talking about.
Right.
Because anyway, I was amazed.
I had the privilege of working with people like that at Bell Laboratories, and the one guy that I worked with, one time we'd jointly written this paper, and so we're off at this conference and we're waiting to present our results, and this other guy gets up and he does this presentation on his paper, and my colleague asked him a question, and the guy immediately stopped in his tracks and realized that everything he'd done in his paper was wrong.
Or,
He didn't go after him. He just asked him a question, but the question was.
yeah, well, that's what they're like. They have this incredible, fast, brilliant mind. It just,
Right.
yeah,
So,
I like the way it shows this apparent hardwiring. And it shows that this is apparently the way the universe is structured.
it's a piece of what goes into, making the universe. It's,
Right.
some people tune into it better than others. Others are, like a Mozart. Mozart, said, well, I just immediately saw the music. What's the problem?
yeah,
Like, a complete symphony. There it is.
yeah.
But there seems to be something objective about it that is knowable.
Yeah,
Maybe
well,
not,
it's a hint that there's a greater order there,
right.
and that we should continue to plug away to try and discern what in the world this greater order is, but for now, we're not there.
Yeah, that's for sure. I'm certainly not.
Yeah. So anyway, I thought this would be an interesting diversion, try and get across. I honestly think he was meditating. He was just channeling this stuff. And, but he was totally hardwired into this collective unconsciousness that's out there. And there wasn't any, it was a gift that he had. How you're sitting there in this village in the middle of nowhere in India, and how in the world does he come up with this?
Right.
You have to ask yourself, there's something else going on here.
Yeah.
So,
That's part of the mystery.
yep. So have a good weekend, Bruce.
Okay.
Do battle next week. Have a good.
All right. Yeah.
Okay, bye-bye.
Take care.
Bye.